Okay, so good morning, everyone. We are happy to have Dr. Curtis Bright with us today. Dr. Bright is an assistant professor in the School of Computer Science at the University of Windsor. He leads the development of MathCheck, a system for verifying and finding counterexamples to mathematical conjectures. His research focuses on computer-assisted proofs, automated reasoning, symbolic computation, and discrete mathematics. He received his PhD in 2017 at the University of Waterloo for demonstrating the effectiveness of combining satisfiability checking and symbolic computation for solving mathematical problems. His works on the first computer verifiable resolution of Lens problem won the Jack Skellner Best Paper Award in 2021, and in 2022, he won an application of computer algebra early researcher award. So thank you, Dr. Bright, with us today, and whenever you are ready.
Thank you so much. Okay, so today I'll be talking about research in SAT solving and lattice reduction for a civics problem called integer factorization. So this is work actually appropriate for this audience because it was based on a master's thesis from last year of Yameen Ajani. So he graduated, he now has a developer position in the government. So next slide. Okay, so who here knows what the SAT problem is? Anyone used the SAT solver before? You guys, I know you used it. So yeah, so it's basically SAT is a very famous problem, right? So if you've taken Comp 1000, right? Some of you may have even taken it with me. We do a lot of logic, right? And we go over the SAT problem. So the SAT problem is given a logical expression, find the way to make the expression true, right? So in logical variables, use true and false. And then you have these logical connectives. So some of them I put on the slide here that allow you to connect Boolean propositions together, right? So just let's go through one example here. So let's say we have this expression x or y and not x if and only if z. Okay, so this is a expression of Boolean logic. Can you make this expression true? Who can tell me if this can be made true? Yeah.
If we set x to true and y to true.
Yeah, if you set x to true and y to true, and then what was that?
So the first clause will become true and the second clause will also become true.
Well, it'll depend on the value of z, right? The second clause, right? Because if x is true, then not x is false, right? And then what does z have to be?
So it will have to be false.
Yeah, z will be false, right? So if you take x and y to true, then as was pointed out, this first expression becomes true. And then if x is true, not x is false. And so z has to be false. That makes the second part true, right? And so the first part is true, the second part is true, then the whole thing is true, right? Because that's how you define and. Okay, so that's exactly this is exactly what the SAT problem is, right? It's a simple problem. Given the expression, figure out a way to make it true. Every formula is going to be satisfiable. There's going to be some formulas that cannot be made true, right? These formulas are said to be unsatisfiable. And so then in that case, if you give that to a solver, the solver is going to return no solution, right? Unsat. And so SAT is a very famous problem, both from theory and in practice. Who here has heard of Donald Knuth? You should have heard of Knuth, right? Knuth is one of my heroes. He's a famous computer scientist, and he's been working on his magnum opus, right? The art of computer programming. He has this prolific series. He's been working for literally 60 years. I looked this up, he started in 1962. Working on it for over 60 years. And he's at age now, and he's as prolific as ever, right? He came up with the last volume, which is volume 4. It's 700 pages, and the second half of that book is all on SAT. It goes very deep into this stuff, right? And you should really check out the book, right? Just it's an excellent reference, for almost all of foundational computer science. Knuth goes over so many. He goes so deep into all these topics. So yeah, stack that up in SAT. Now, the interesting thing about SAT is it's known as what's known as an NP complete problem. So for those of you who's taken or will take 4540, right, the 400-year algorithms course, they'll talk about NP completeness, right? NP complete problems are essentially problems like SAT, where nobody has an efficient polytime algorithm to solve these. In fact, it's conjectured there is no polynomial time algorithm to solve SAT or any NP complete problem. Okay, so this is not a proof, but the conventional wisdom is that SAT in the worst case is going to be inefficient to solve. Right, the best algorithms are exponential time. Now, despite that, the curious thing about SAT is that there are actually effective SAT solvers that, in practice, will solve problems that arise that many people care about. Right? This comes from, I'm going to give you many examples, but it comes from industrial problems. It also comes from problems that you might have done. Who's played Sudoku before? Really? Only a couple? You know what Sudoku is, right? The game and where it's a grid of numbers. You have to fill in every square with a number 1 through 9. And there's some rules about, yeah, okay, people know, right? You can't repeat any number in any row, column, or any block. Right, so you start with some numbers filled in. You have to try to fill in the rest of the numbers subject to those constraints. This Sudoku is essentially a problem that can be solved by a SAT solver because you can reduce it into a logical formula, right? And you can give the logical formula to a SAT solver, and it'll solve your Sudoku for you, right? So you don't have to spend the time and do it yourself. All right, so I'm going to start about 4 applications of problems where I chose these problems because they're not logical problems. They're actually pretty interesting problems, I think. So here's the first. Anyone heard of this aperiodic monotile called the hat? Anyone seen this? So this got around popular press a couple of years ago because it solved a long-standing open problem known as find an aperiodic monotile. This is a tile that can tile the entire plane, right, without any gaps or overlaps. So it tiles the entire plane, and it does it, but in a non-periodic fashion. So you can obviously tile a plane with squares, right? You just put a bunch of squares next to each other, like you go to a room, you can see a square tiling. It goes up to infinity, but it does it in a periodic fashion, right? Because the squares just it's periodic. But with the hat, the cool thing with the hat is it tiles the entire plane, but it does it without any repetitions, right? So here's just an example of what a tiling would look like, and it's a famous problem to find, does such a tile even exist? Some people thought it didn't exist. Some people thought maybe it exists and we just didn't find it. Well, it turns out it does exist. And this was, many decades of people looking for this tile. And the cool thing was we actually found the help of the SAT solver. So what they did essentially was they reduced the tiling problem into a SAT formulation. And then we used the SAT solver to look for tilings. Right, so this tiling here is actually constructed, I believe, with a SAT solver, and it basically is 1 half surrounded by 16 layers of hats, and you give this, you reduce it to SAT, you give it to the SAT solver, it finds a solution, which is then translated into a tiling, or it might find there's no solution, which would then be proof that there is no tiling, right, for a certain tile. Anyway, so it's a really cool success story. You can read the paper. And Craig Kaplan, who is professor at Waterloo, wrote an interesting article in the Scientific American about the kind of the journey they went on to find this thing, because it was an interesting way they found it. Okay, this is what I did as a postdoctoral researcher. This is on projective planes. So projective planes are these fascinating mathematical structures. You basically have a collection of points, you have a collection of lines, and you have a very restrictive condition. You have any 2 lines meet at a unique point, and you have any 2 points define a unique line. And so with those restrictions, you can come up with some simple small examples. So here's an order 1, 2, and 3, where you have 2 points in the line, 3 points in the line, and 4 points in the line. And you have to cheat a little bit. You can't use just straight lines, right? You have to represent them visually. I made some of the lines curved in order to, but as long as you have the fixed point that any 2 lines meet at a unique point, and any 2 points define a unique line, that's a projective plane. Now, mathematicians have studied these things for least 100 or 200 years. And a big question was from when do these objects exist? It's still today, but we know they exist in prime power two, and we know existence in order 6. The first open case was order 10, and this was known as Lamb's problem. So Lamb was a mathematician who actually solved this with a big computer search in the 80s. And we were actually able to verify the search with a SAT solver, right? So you reduce the problem to SAT, you let the SAT solver do its search, and it comes out and says unsat. This is a proof that the corresponding plane doesn't exist. Okay, so the SAT solver is good at both searching for things, but also proving the non-existence of things. If you can reduce your problem to SAT. Here's another one. Again, that's kind of a geometry problem. This is a question of Erdos. So here, Erdos asked if you have a large set of points in the plane, we're going to say that no 3 points are on the same line. So you have a bunch of random points in the plane. Is it necessary that there must exist a K-hole, right? A K-hole is a convex polynomial that doesn't contain a point inside of it. So here's an example. Here's 3 examples of 4 holes, right? So this is a 4 hole because it's a quadrilateral, 4 points, but there's no point inside, right? Each of these has no point inside. And the question that Erdos asked is it the case that there always must exist a 4 hole if you have a large enough set of points? And it's true. If you have 5 points, as you can see here, these are each 5 points. Each of these has a 4 hole. In fact, any set of 5 points is going to have a 4 hole. In fact, any set of 10 points is going to have a 5 hole. And you might think, well, by generalization, as take enough points, you're always going to have a large enough, K hole. It's not true. You can actually, there are very large sets of points which do not contain a 7 hole. Everyone has been surprised, right? So math doesn't always work out the way you think. So the question is what happens to 6 hole? This was actually, the best result was just found last year. They actually showed with the SAT solver that for 6 holes, you can have 30 points, you guarantee you have a 6 hole. If you have 29 points, there's sets of 29 points without a 6 hole. Right? So 30 is the magic number there. And so this was again, problem that was solved with the SAT solver, right? The SAT solver, the hard here is to find that every set of 29 points, every set of 30 points must have a 6 hole, right? So again, the SAT solver did that search. This is one of them. So John Huey, another famous mathematician, right? He actually passed during the pandemic, unfortunately, but he was, did so many cool things in his career. One of the cool things was called the free will theorem, which was with Simon Colloquium. So here's a photo of them together. And you don't hear mathematicians proving things about free will, right? But John Congo isn't an ordinary mathematician. So what he did, so how did he define free will? He said essentially, you have free will, there's no function which is going to predict what you do next, right? So if you take a function which takes the state of the universe currently, and if there's a function which predicts the next state, then that's determined. If there's no function, then that's free will, right? It'll prove that if a quantum particle has free will, then, if humans have free will, so there is some free will, then actually even the quantum particle will have free will. Anyway, so the proof uses some principles of quantum mechanics, and it also uses a combinatorial argument, which is what we're interested in here. So on the right, they use this set of 31 vectors in 3-dimensional space. And, it's a specific set of 31 vectors that they use to make their proof work. And the question we asked was, well, can you do better than 31? Right? So you can do the proof with 31 vectors, but maybe you could use a smaller set. We weren't able to find a smaller set, but we were able to prove some lower bounds. We actually showed with the SAT solver that you must have at least 23 vectors in a KS set. And actually we extended that even to 24 vectors. So again, what you do is reduce the problem to SAT and say, okay, we're looking for 24 vectors which satisfy these properties that a KS has to satisfy. And then it either finds one, which by finding the satisfying assignment of the formula, or it shows there's no satisfying assignment, which then proves a lower bound, right? This KS set with 24 vectors doesn't exist. And I can do an entire talk or an hour just on cool applications of SAT. I'm going to focus on one application, which, as I said, with integer factorization. But I wanted to list just some other cool ones, especially because so the first 5 points here are students of mine at Windsor who are working on SAT. In fact, some of them are in this room. Right. So we have Aaron Barnum who did a published paper on minimizing finite automaton. We have Sadman Sakil, who is working on dependency resolution when managing packages. Last year, Malian and Alamgir worked on finding collisions in hash functions. We have Yameen Ajani, who is finding new shard numbers, and Amdu Gita researching for Lattice squares of certain forms with the SAT solver. And then there's many other cool applications. For today, we're going to focus on one application, which is to cryptography and integer factorization. Okay, so Yameen, this was work that he did, and he graduated last year. So who here has seen the RSA crypto system or knows of RSA? Okay. So essentially, if you're going to be buying something on Amazon, right, everyone's had this experience probably. I mean, what do you have to give Amazon? Your credit card information, right? Because they're going to charge your card, and you don't want someone who's snooping in over the wire to get that information, right? Maybe you have an eavesdropper, right? Your ISP or somebody who's put a wiretap on your internet connection. You don't need them to get your credit card information. So what happens in practice is it is encrypted in a format that only Amazon can read. Okay, so Amazon has this public key that they publish, so everyone knows it, and anyone can now send things to Amazon in a secure way by using that public key. Only Amazon is the one who has the key to unlock that encryption. Now, the way this works for RSA, which is a popular crypto system, it's still used in practice. It's over 50 years old now, and seems to be secure for the time being. It's based on the problem of integer factorization. So this is the classic problem from number theory. You're given an integer, factorize it into primes, right? There's a unique way to do this. This is proven by Euclid like over 2,000 years ago, right? There's a unique prime factorization. We're going to actually focus on primes of a specific form called semi-primes. They have exactly two prime factors, right? So you take P, you take Q, these are two large primes, just random primes, multiply them together to get N. This is your semi-prime. And this is essentially what Amazon does, right? So they publish this N, which is the product of two primes that only Amazon knows the primes in N, right? The primes that make up N. Now, Amazon can easily do that because they can just choose two random primes, do the publication, and get N. But now, when they publish N, if we want to break the crypto system, we have to go backwards, right? We have to find the primes that multiply to N. This is a very difficult problem because there's so many large primes, huge numbers of primes, right? So it's a very hard search to do the opposite direction, right? Multiplication is easy, but factoring is difficult. The best attempt that I'm going to say involves factoring in, and there's no efficient integer factorization algorithms for N, except there is a curiosity here. Integer factorization is very interesting because there's a quantum algorithm. So people have probably heard of quantum computing, right? Quantum computing is this, hot topic. People have been studying it, and there's still in the race to build a quantum computer, right? In fact, Google, it seems every year there's more announcements in the popular press, but okay, here's the bigger quantum computer, right? They did a bigger computation. One of the reasons why quantum computers are a hot topic is exactly because it would allow you to break RSA by factoring N, right? There's an efficient quantum algorithm, right? It doesn't run on classical computers, but it runs on quantum computers. So it's very fascinating, right? That I don't think anyone would have expected that, but sometimes it's like reality is weirder than fiction. All right, so let's go quickly the reduction of factoring to SAT. So how do you actually come up with a logical formula that will allow you to factor numbers? Well, it's actually pretty straightforward. In fact, people who've looked at circuits, right? Probably most people here have looked at circuits, right? Like binary circuits, Boolean. You can build a little circuit which basically does a computation. What we're going to do is essentially build a multiplier circuit, right? A multiplier circuit which just takes two inputs and it multiplies them. We just do this, with the school book multiplication method. So here's how you can do it. Let's say N, the number we want to factor, has 4 bits. In actual practice, it's going to have thousands of bits, right? But let's say it just has 4 bits. And they're N3, N2, N1, and 0. That's the binary representation of N. And let's say the variables in P and Q each have 2 bits, right? So P0, P1, Q0, Q1. And then we multiply together to get N. So what do we do? So you can set up a simple multiplication problem here, right? You have bits of P, you have the bits of Q as input, You multiply them together, you do some additions and carries and so on, you get the bits of n. You know the bits of n. That's what you're trying to factor. Okay, so essentially it's a multiplication problem where you fill in the digits. It's kind of like a reverse multiplication. And what you can do is relate all the variables in this. You can see like a puzzle where you have a puzzle book where they ask you to give you some digits here, they want you to fill in the other digits. Well, it's exactly what the stat solver is doing, right? Except the stat solver only takes logical expressions, but these equations can easily be converted into logic. Like as an example, you have A0 here as a product of P0 and Q0, right? That's just how you define A0 in the multiplication. Well, what we could do is say if A0 is true, that means P0 is true and Q0 is true, right? Because 1 times 1 is 1. Whereas if A0 is false, then either P0 is false or Q0 is false, right? Because 0 is equal to 0 times 0 or 1 times 0. And so you basically can come up with logical expressions which define all these equations. Then you can convert those, you take those expressions, give them to a stat solver, right? Because a stat solver takes as input logical expressions. You also give the stat solver the bits of n, but not the bits of p and q, as you don't know those bits. But that you have a logical formula that the stat solver is going to try to solve. It's going to try to find the bits of p and q for you. And you can do this, right? You can actually do this. It's going to work, except it's only going to work for small values of n. It's not going to scale. And this is a quote from Canute's computer programming. He basically said, yeah, this is kind of mind-boggling when this even works, right? Because you're not using really any cleverness in a sense. You're just taking the multiplication circuit and just converting it into logic, which then you just throw in the stat solver and get it if the search space is small enough. But it's not going to scale. It's not because it's not using any kind of number theory that we can exploit, right? Not a computational number theorists have come up with really fast ways of factoring. Well, not fundamental time ways of factoring, but ways of factoring which are much better than just a brute force search. In fact, the best known factorization algorithm today is called the number field sieve, and it can factor an n-bit integer in approximately e to the q root n. So this OTL essentially just means big O to ignore the logarithmic factors. So if we're going e to the cubed root of n, this is going to be worse than any polynomial. It is better than just a pure exponential though. So it's better than what a stat solver can do. The stat solver is going to be blown into the water with the number field sieve. Okay, so it seems like it's a nice idea, but it doesn't work right in practice because the stat solver is going to fall on its face when the numbers get too large. Okay, but this brings me to what I call the Achilles heel of cryptography. Right? The Achilles heel of cryptography is that it has to be done in the actual real world. Right? The mathematics behind the crypto system is perfectly secure, but that's not the end of the story, right? To actually communicate with someone, you actually have to implement the thing. And that is actually where things go awry in practice, right? It's like when you see this leak of like a big company or something, there's always these data leaks, like, oh, billions of records have been leaked by some hackers. It's not the underlying crypto system, it's the implementation. There's information which is leaked in practice, right? There's these side analytics, right? Maybe it's a social engineering attack or even doing a timing attack. So cryptographers have developed really underhanded ways of learning information that they shouldn't have to learn, right? Like bits about P and Q can be leaked by just timing how long the encryption takes, right? You ask someone to encrypt this message, and if you're able to time how long it takes, you might actually learn facts about the private key that you shouldn't know. I'm going to talk about one specific side channel attack that will motivate other. So let's say, here's the motivating example. Let's say you have a full disk encryption. Okay, so we'll use an RSA and you encrypt all the files on your disk. Right, so that means that an adversary, they steal the drive. It's useless to them, right? Because they don't know your private key. So if you want no one to read your emails, right, you were gonna use full disk encryption, and you're gonna keep your private key safe, right? And also you're doing like screen locking, right? So even if somebody, they steal your laptop while it's running, they can't read your email because they can't get into your operating system, right? Even though the Achilles heel of the scheme is that your computer has to know the private key, right? And for the computer to read your email, you have to type in your password or whatever to derive the key, which is then stored in memory, so that you actually can read your email, right? But if someone steals a hard drive, it's no good to them. And the memory is no good to them too, right? Because if they take that out of your machine, they cut the power to it, they lose all the bits in the RAM, right? So even if the key is somewhere in memory, even if they have physical access to your machine, it seems like they can't get the bits of the private key. However, that's actually not true. And this is a surprising attack that was published in 2009 called a cold boot attack. And it's a little bit of a cold boot attack because what they did was they took the RAM module and they stuck it in liquid nitrogen, right? So they cool it down to like almost absolute zero. That actually prevents the bits from they maintain the state of the RAM, even though it doesn't have power, right? So they steal the computer, take the RAM out of cut the power, put it in liquid nitrogen. That's going to preserve the bits of the RAM, which then they can put into a computer they control later on, right? And then get the bits of the private key. Now it's going to be a degraded copy of the bits because some of the bits are going to decay. But it's a bit surprising to me, right? 99% of the bits in the RAM module was actually recoverable after an hour without power, right? Assuming that it was stored in liquid nitrogen. If you don't cool down the RAM, the bits are going to decay very quickly, right? After a second, all the bits are going to be lost. So you have to cool it down to be very cold, and then the bits are going to be preservable, at least some of the bits, right? And so first, what actually happens in practice, the bits are going to start to decay, right? As soon as you add the power to your RAM, the bits are going to decay slowly at some rate, right? Let's say they decay to a ground state, so it's decayed to zero. So the bits that are going to start to slowly decay to zero as they lose power. Now, this actually tells you something about the bits. Let's say we're James Bond, right? And you're breaking into Dr. Evil's lair, and he has plans to destroy the world, encrypted by RSA on this hard drive, right? But you steal the RAM, put it in liquid nitrogen, you take it back to Q. Now, Q, in order to save the world, has to figure out the bits of P, right? The bits of the prime to reveal the plans. What happens is some of the bits have decayed to zero, some of the bits, however, remain one. And the bits that remain one must have originally been a one, right? Because bits don't decay to one. So if it was originally, if it's now it was originally one. If it's now zero, it may have been originally zero, or it may have been one that decayed to zero. So you don't know. However, what we do know is essentially at random bit positions, right? So here's a schematic. The red bits here are bits. These are the bits of P. At random positions, we've learned known bits of P, right? The red bits are ones that we know will be a one. So the white bits might be zero or might be one. We're just we maybe know some probability, but we'll say no, unknown, they're unknown. But for sure, we know. I think is it made about like this? For sure, we know the red bits here, right? And the point is they are at random bit positions. Okay, so how do we do this, right? How do we stay in the world? How can we derive the remaining bits? So there's too many unknown bits to check all possibilities, right? So brute force is not going to work. So the thing that we might also try is the number field sieve, of course, right? Because the number field sieve is the fastest general purpose factorization algorithm. We know that extra information now, right? We know these leaked bits. The thing about the number field sieve is it doesn't seem to be, it doesn't help the number field sieve, right? This leaked information doesn't make it any faster, unfortunately. You would like to be able to exploit this known information, but it seems like number field sieve it works on a different structure, doesn't seem to be possible. If you're looking at the SAT solver, the lead bits will absolutely help the SAT solver, right? Because remember, the SAT solver has an encoding of all the bits of P. So if you know the bits of P is a one, you just go to that variable encoding that specific bit, and you just say that variable is true, right? If it's a one, then that's represented by true. If it was zero, it would be represented by false. So anyways, when you have root information about the bits, you can give that information to the SAT solver, and the SAT solver is going to speed up the search, right? Because if it knows one variable is true, it's not going to try a false for that variable, right? It's just extra information it can use, and in practice, it will dramatically speed up the SAT solver. However, remember the SAT solver does not know any number theory. It's just operating blindly, right? It's just looking at the circuit that you give it and the leaked bits you give it, and it's just trying to find a solution, right? What we wanted to do was to use algebraic methods, maybe like the number field sieve sort of structure that is algebraic, to improve the SAT solver. So the way we actually deal with it in practice is this method called Coppersmith's method. So Coppersmith he's a mathematician who came up with this really cool method of factoring numbers when you have leaked information about the numbers. I won't go too deep into the math behind Coppersmith. I tried to really keep it at a basic level. I'll give you a summary of how Coppersmith works, but here's what it does. If you have one of these two cases, right, where the bits of P, you know the lowest half of the bits of P, or you know the highest half of the bits of P, right? So one of these two cases, you can derive the unknown bits in polynomial time. So we know half the low bits of P or half the high bits of P. The other half can be found. And the way Coppersmith does this is by two algebraic techniques known as polynomial root finding and lattice basis reduction. Okay, so these are both things that you'll study in like an algebra course. Let me just start. I'm just going to go over briefly what these are. So lattice basis reduction, what's the lattice? So lattice is essentially a point, set of points in Euclidean space. So here's just a two-dimensional lattice, right? And the points in the grid here are all here. They form a lattice. They're generated by these two vectors, right? So this vector here, this vector here, these are the red arrows. They generate the lattice, right? Because you just take any combination, integer combinations of these vectors, you can get to any point. You might have to take negative combinations to get down here, right? But you can get anywhere in the lattice with this these two vectors. They're called the basis of the lattice. You can generate lattices also with polynomials using like a correspondence at the bottom here. So a polynomial of degree 3 has 4 coefficients here. If you stick those coefficients to a lattice vector, they're going to generate a lattice, right? So Coppersmith is going to use a polynomial lattice, right? So it's just a two-dimensional lattice. Of course, you can go 3-dimensional lattice, 4-dimensional lattice, and so on. Okay, so why are lattices so widely used? One of the reasons is because there's a nice computational way of what's known as reducing a lattice, which means essentially find short lattice vectors, right? Even if your basis is consisting of long lattice vectors. So here's better to look at an example. So this is the same as in the previous slide. In fact, the same two red vectors which generate the lattice. But you might actually be surprised that the blue vectors also generate the same lattice. They're what I call a bound basis, right? Because to get to a point over here using the blue vectors wouldn't be so easy, right? You have to go way off the screen over here and then come back using a different vector. So it's much easier to just use the red vectors to get to a point rather than the blue vectors. So they do generate the same lattice. What LLM will do, is the famous lattice algorithm, will take that basis, like the blue vectors, and translate it into a good basis, the red vectors, right? The good basis consists of short vectors, whereas the bad basis consists of long vectors, although they do generate the same lattice. Okay, so that's how we can find short lattice vectors. Now, Coppersmith, this is my one-slide summary of Coppersmith. Coppersmith does something, his method, it's a root finding method, it's hard, but it's almost miraculous because it finds roots of a polynomial mod p, where p is unknown, which seems, how the heck could you possibly do that, right? Because you don't know p, right? You can find roots of a polynomial over the reals, you can find roots of a polynomial mod p, where p is not. Right, if p is a known prime, this is a well known how to find roots mod p. But if p is unknown, we know a multiple of p, namely n, right? N is p times q. Coppersmith actually allows you to find roots mod p, small roots mod p. So they have to be small, but it allows you to find roots mod p, even if you don't know p. So how does he do this? So Coppersmith, basically what Coppersmith does is he compares a problem of finding roots mod p to a problem of finding roots over the reals. He generates a new polynomial which is going to share all the same roots mod p, but the roots are now going to be over the reals. And we know how to do real root finding. Okay, so it's essentially a reduction to a real root find, and also finding a short vector in the lattice. So what does this have to do with factoring? Well, you can set up a factoring with known bits problem as a root finding problem, which is shown on the slide here. So let's say p is the prime that we want to find. It consists of high bits and low bits. Right, so it's going to be p hat plus p check. P hat's the high bits, p check is the low bits. let's say we know a lot of high bits and we don't know that, and we want to find low bits and there's a limited number of them. Right, so an example, which is kind of an extreme example, but let's say we know almost all our bits of P, it's 75, 80, and the low bits of P, we just don't know 3, right? So there's 2 bits here encoding the low bits, just the number 3. Okay, so we want to find the low bits given the high bits. So what you can do is you set up a polynomial. It's just going to be a polynomial P hat plus X, and we have X as a solution of this polynomial mod P. Right? Because if you solve an X equal to 3, you get P itself, which is 0 mod P. And so what Smith does is tries to find roots of this polynomial F mod P. We don't know P, that's the hard part. But what he does is he sets up a lattice. So again, this is the F from the polynomial from the previous slide. You can generate copies of multiples of F with M. This is the lattice he uses. The point is, if you can find a short vector in this lattice, Smith shows, that short vector is going to correspond to a polynomial that has the roots the bits that we want as a real root. Okay, I'll just show you in practice what happens. So here's LOL. This is the lattice basis, the bad basis that you give to LOL. When you use LOL, this is the basis that you get. So it kind of smooths out the numbers, right? So this is actually going to consist of shorter vectors. The first vector corresponds to a polynomial shown here, which has 2 real roots, 2 integer roots, 3 and 43. 143 is just a spurious root, doesn't help us, but 3 is the bits that we want. You solve in 3 into your polynomial, you get the prime factor. Okay, so it's a very simple case, right, with small numbers, but that is how Smith works. Sets up a lattice, finds a short vector, and then finds the roots of that vector over the reals, which then gives us the roots mod P. Okay, so it looks like time, but the problem is it doesn't remember the case that we were wanting to solve was where the bits that were known were random positions. They weren't a single large chunk like the 50% high bits. They were random, maybe we don't 50% of the bits, but they're randomly distributed amongst the primes. So Coppersmith doesn't apply in that case. You can generalize Coppersmith so that it gives you, it can work when you have multiple chunks of known bits, but it's going to be exponential in the number of chunks, which essentially makes it infeasible to run when you have lots of chunks, right? We have, in practice, it's going to be lots of chunks because there's just random positions, right? We don't control how many chunks there are. So Coppersmith doesn't apply in this scenario. But what we can use is we're going to use Coppersmith as a subroutine. Here's how it works. We're going to hook it up to a SAT solver. So the SAT solver, it works kind of like playing Sudoku. All right, the SAT solver is making guesses. Right? If you've ever solved a Sudoku, you probably had this experience, right? You're solving, okay, you derive some numbers, you reach a state where you can't drive any farther. But you still have cells to fill in, so you make a guess. Right? You know that this cell must be a 3 or 4. Well, you assign, let's take a guess, it's a 3. And then you can keep going, you can progress a little bit farther, and either you find a solution, solve the entire Sudoku, or more likely, what happens in practice is you made an incorrect guess. It actually wasn't a 3. So you have to back up, you have to erase the things that you just derived and then start over from now on, assuming 3, but it's 4. You keep going on, and that's what the SAT was doing, except with trues and falses, right? It's making some variables true, some variables false, and eventually it's going to either find a solution or it's going to determine I made an incorrect guess, backtrack. But here's the thing: at some point, the SAT solver is going to make guesses for, let's say, all the bits of P. So every bit of P is a variable. Let's say we know all the bits. We know the bits are. We guessed the low bits to be 1.000.101. What do we do? Well, the SAT solver can just now start guessing variables for the higher bits of P, right? It would start guessing values for these bits. But if you know Coppersmith, you have Coppersmith in your back pocket, what can you do? This is 50% of the low bits, right? Coppersmith will now reveal the high bits in polynomial time if those low bits were assigned correctly. So there's 2 cases. If the low bits were assigned correctly, Coppersmith will give you the high bits efficiently in polytime. You made an incorrect guess. Right? The solver, one of these bits was not assigned correctly, in which case, well, now Coppersmith is going to fail, right? There's no way to extend these low bits if they were assigned incorrectly to high bits. There's no prime of that form. Coppersmith is going to tell you that. It's going to say, failure, couldn't find any high bits that work. But that gives you information. Even though it's a failure, it gives you information because now it tells you you must change one of those low bits. You made an incorrect guess. And the solver would eventually learn that. It would eventually learn you made an incorrect guess, but it would take it a while, right? We have to basically assign values to all the other high bits until it learned that. Whereas now we can backtrack early. Coppersmith, even though it failed, gives us information that we can use to speed up the search. At least that was the thought. And it turned out that actually works in practice. So this is the data that Yameen generated. Basically, you generate 15 minimum instances for varying bit lengths, and starting about 128 bits, going up to about almost 2,000 bits. And you just ran them for 3 days with the SAT solver, with both the SAT with Coppersmith applied, and also the pure SAT approach. So the pure SAT approach is the orange line. Each dot is the running time, and the solid line is the median of the 15. And then the blue line shows you what it's SAT with Coppersmith. And you can see this is the log scale. So the gap between the two is actually, in practice, an exponential size gap, right? So even though the running time is also exponential, the speed of it is also exponential. So you're able to solve quite a lot higher problems. You're able to solve, even cases up to almost 2,000 bits, whereas the SAT solver was kind of topping out around 1,000 bits. Okay, and just to compare the number of field sieve, which again, remember the number of field sieve is going to be slow because it doesn't use the leaked bits at all. And we're way faster than the number of field sieve in this case, right? Because like for 512 bits, number of field sieve uses about 3,000 hours to factor in, whereas we can factor it in with the SAT solver and put 1,000 seconds. And with Coppersmith and SAT, we were able to factor in about 100 seconds. So a huge speed out there because we're exploiting the leaked information. This is just kind of flipping the what we're measuring. So this bits tend to be 256 bits, and we vary how much of P and Q we leak. And you can see again, the SAT solver tops out around 45% leaked bits, whereas with Coppersmith you can go up to 35% leaked bits, so less leaked bits, right? So the problem's harder. We're still able to solve it, although the running time really starts looking quite bad, right? It kind of explodes around 40% leaked bits. And interestingly, we compared this approach in the literature, which was the only code that we found that actually could solve such problems. The approach was a branch and prune approach, but they were able to show, subject to some assumptions, that there's a theoretical result that they can actually show 57% is a kind of cutoff, where if you have more than 57% of the bits, you actually can solve it in polytime. If you have less than 57% of the bits, it's going to be an exponential time search. And so what we did was we ran our code, we actually had an implementation available. We ran it even with less than 57%, so it's going to take exponential time, but we could compare against it. And for example, 40% leaked bits, their code was taking around 2,000 seconds, and we were taking around 100 seconds. Right? The way we wrote them was they were actually storing all the branches in memory. And then because it's an exponential number of branches, it blew out their memory usage. They're using 90 gigabytes. One of the secret sauces of the SAT solver is actually the memory usage. Right? SAT solvers, modern SAT solvers are very good at keeping their memory footprint low. Right? That just makes them more efficient because when you have a huge amount of memory, it slows everything down. So SAT solvers never use more than half a gigabyte in these instances. Okay, so that's an overview of everything. I just want to sum up and say that I've been working this for like 10 years now, hard to believe. Just combinations of SAT and computer algebra. And I've seen this is not an isolated incident. This happens in many different problems, right? It's the type of problem where you have some kind of search where the SAT solver is very good at search, right? It's kind of unstructured, right? You have a bunch of constraints that you have to search through. SAT solvers are very good at those types of problems. On the other hand, many problems also have mathematical structure that you want to exploit too, like factoring. It's lots of mathematical structure that the SAT solver doesn't know, but the computer algebra system can implement things like lattice reduction and polynomial root finding. For problems of that form, this is a perfect example of synergy between SAT solver and computer algebra, right? You want them both because you're able to get this fast search and you're also able to get the sophisticated mathematics. Right, so many problems that I've worked on actually have this flavor, and we typically see exponential time speedups. right? Even though the surface is inherently exponential, the speed of it is also exponential, meaning we're able to solve larger search spaces, right? Larger examples of problems. So I wrote a survey article in Communications of the ACM a couple of years ago. If you're interested, you can check that out. A lot of other examples on my webpage. And happy to take any questions now. So thanks all for coming out.
Okay, any questions?
Just in, yeah.
Thank you. It was fascinating. My question is, what is the worst case time complexity of your algorithm?
Yeah, so one the complexity, there's no provable result, right? Because stat solvers are going to be exponential time.
It's exponential, right? It's sub-exponential.
The stat solver is exponential.
Is it better than the last known integer factorization?
No, so because the integer factorization method feels that that's sub-exponential. So in theory, we can't beat that. Right? We don't know how to. Like maybe there's a polynomial factoring algorithm, but we don't have one. So basically, the thing about SAT is it's not kind of it's a theory that doesn't come up to practice. Right? SAT solvers we're using them as this tool, which are effective in practice, but this theory isn't there, right? The theory just says SAT is exponential time in the worst case. We don't have a better bound than that.
So your program essentially is a Wolfram formula in proposition logic, right? How many variables you create? Must be millions.
Well, I don't think our examples were millions. There are other examples where you have millions of variables. In our examples, right, say 1,000 bits in your you want to factor 1,000-bit number. You're probably going to have about 1,000 bits representing the primes. You're going to have some extra bits representing you form a multiplication circuit, right? And you have some extra bits representing the carries and all the variables in your multiplication circuit. But that one's going to be a polynomial number. So it'll probably be, 1,000 squared or something like that.
Then how do you create that? 1,000, that still take a while to type or automatic?
Oh, it's automatic, yeah. You don't create it.
Yeah.
You just write like a Python script, which we're going to create the logical formula for you.
So you a variable is not V1, V2, probably just integers, right? So you want to show us, is it possible to show us a program and some, take a look?
Well, it's like the code is available, right? So you can download the program and look at the instance if you want, yeah.
Now, what is the largest integer you can factorize?
Using our approach?
Yeah.
Well, it depends on if you want to leak, how much you leak, right? So 50% leaked bits, it kind of tops out around 1,700 bits.
How many?
But with more leaked bits, right, we can go farther.
How many bits roughly?
Well, it depends on how much you leak, right?
Oh, the leak, I see. So the largest you have been able to break is 500.
In this case, it's around 1,700 bits.
Oh, that's good. So, no, I think it's not somewhere. It's okay. Thank you. Thank you. Very good.
Thank you. Any other question? Oh, yeah, go ahead.
Okay, yeah, I was just wondering, I couldn't remember, could you use like cube and conquer or any kind of parallelization techniques for this one? Or
Well, you can, of course, but I think it might be hard to parallelize this. I mean, you can obviously do a naive parallelization, just choose a couple bits that you split all the possibilities on. I guess it would speed, in this case, there's only one solution, right? So you probably could speed things up by, if you have n processors, maybe speed up by a factor roughly n.
Okay.
Yeah, we didn't try that.
okay, and like, so calling like the coppersmith and all that's not a problem with cube and conquer, like it's just a bunch of instances all separately running their own little like call.
Yeah, it might be a problem in getting an even split.
Okay.
Because the splitter would know the theory behind it.
Okay.
I was wondering, I mean, if all the bits are unknown, then, I mean, is there any way to solve this problem?
No, so that would be no root information. And then the stat solver is not going to perform well at all. Like I said before, the number field sieve will be way faster because it's sub-exponential time. Where the stat solver, it will run in exponential time in that case. Right? Like in some certain cases, it seems to run much better than exponential time, but those are specific problems where it's able to learn some kind of. It's an open research question, right? Like I said, the theory hasn't caught up. Why are stat solvers so effective on certain classes of problems? It just in practice, they're able to exploit some information that makes it better than exponential time, but we don't have a quantifiable result there.
Thank you.
Any other question?
There is online, it seems, I see here. So I don't know, can you maybe unmute yourself?
Are you talking about me, Dr. Brett?
Yeah.
Yeah.
Yeah, sure.
Yeah. So I was going to ask, are you planning for some future work with respect to the stat solving specific areas in it?
So what was the last part?
Oh, so are you specifically looking at, so what are your future plans with your research right now?
Oh, yeah, I'm looking at other problems. Like I said, some of my students, there's lots of problems where stat solving couldn't be, like I can figure a variety of problems, right? Like problems where the stat solver, they're not problems in logic. So a lot of them, it's surprising you can apply the stat solver to that. But there are graph problems, right? Searching for certain types of graphs with structure, if you can code that structure to stat. But yeah, it's not nothing like specifically that I have for you.
Got it. Okay. So nothing with respect to the performance improvement, but applying it to different areas is what you mean.
Yeah, I often try to, people come to me with like, oh, can you solve this problem with the stat solver? It's like, okay, well, let's see. Right? And sometimes you don't know until you try, right? Sometimes I'm often surprised, either in a good way or a bad way. Sometimes, I think, oh, this will be a great stat for a stat solver, and you try it, it just falls in its face. And other times, I'm thinking, oh, there's no way the stat solver is going to do well on this problem, and it actually does surprisingly well. So yeah, there's weird things about the stat where they're good at certain problems that you might not expect.
That's good. Okay. Thank you, Dr. Brett. Yeah.
Yeah, thank you.
Any other question? Okay, so if there is no other question, so let's thank Dr. Bright again.